All right, cool. And I think we're live. So what's up, everybody? Welcome to the first sponsor workshop that we're doing for the Grants Round 11 hackathon. I'm here with Bernhard from Fluence. We're going to be talking a bit about their bounties, their tech, and IPFS and Aqua and some other fun stuff. So just let me send out a quick alert for people to join the session here. And yeah, I guess Bernhard, I'll watch. If you guys have questions out there, I can ask them for you. Just drop a note in the chat. This is also streaming to YouTube. Everything will be recorded. So, yeah, Bernhard, do you want to introduce
All
yourself?
right. I'm. Let me just try to get the share done here. Then I'm good to go. All right. How does this work? All right. So okay, I don't see myself. All right. Okay.
Yeah,
I'm. Do you see it?
Yeah. Do you want a full screen? Oh, yeah. There you go. Yeah, perfect.
All right. So yeah. Okay. I don't see myself. So now I'm just talking to the title. That's unnerving, but done it before. Hi, everybody. Hey, Connor. Thanks for having me. Thanks for being here. And I'm Bernhard. I'm with Fluence. And today I want to talk a little bit of workshop on programming decentralized compute and IPFS with Aqua. And then, of course, go over the prizes and sort of how to ramp you up and get you the best start into that what's going to be obviously a super amazing hackathon. So a little bit about Fluence. Fluence is a permissionless and secure peer-to-peer protocol, and the protocol really focuses on compute. And as part of the Fluence solution, we have a network, or the stack, we have a network and a bunch of open source tooling. And that bunch of open source tooling is something we really need to talk about during the workshop. The way things work on the Fluence network is that you create WebAssembly modules where it's WebAssembly interface type, not BindGen, which you probably might be more familiar from the browser side. And those modules then execute on a runtime, which we call Marine, which is available on each network peer. The way the addressability of those modules works is actually you link them into logical constructs we call services. And those services, despite being highly sandboxed as WebAssembly modules, actually can execute external effects. So you can download, upload, modify, replicate, and you actually can use HTTP. As you know, or most of you know, in WebAssembly, you don't have sockets, you don't have async, and WebAssembly IT is highly sandboxed. So it takes some trickery to make all this stuff secure, but HTTP is available, and we actually have file storage. And in addition, with those services, you actually can create connections or adapters to services already available outside the Fluence peer-to-peer network. So, for example, IPFS comes to mind. Any microservice you can think of and any API that's out there, you can basically wrap and bring into the peer-to-peer network flow. The way you program services in Fluence is with a purpose-built language called Aqua. Now, before we go any further there, let me, let's see. If you look at the right, there's this little teeny weeny little peer-to-peer network, and it's got two clients, the green ones, which could be, and then a bunch of peer-to-peer nodes, and those nodes host services, one or more, could be any one or more. A relay, by the way, is just a node that's publicly accessible. It's not all nodes necessarily, peers are necessarily publicly accessible. And am I doing something wrong? I just hear beeping.
I hear that too. I'm not sure where that's coming from.
All right, I'll just keep going then. and services, yes. So we have the services, one or more. A relay node is just something that's publicly accessible because not all nodes actually are publicly accessible. They could be behind NATs, or it could be a browser. A browser itself is not directly accessible as a peer, has to go through a relay. And if we look on the continue with there, one of the services is a representative of an adapter service that links you to all those other services available.
We're not looking at the presentation anymore, Bernhard. I'm not sure.
Let me see what it's...
Maybe. Wait, I am still hearing the beeping though. I'm like, it's
okay. My beeping is gone.
Okay, yeah, it stopped. That's good.
Okay, and do you still see the share or?
No, I think you need to reshare.
Okay, the share disappeared. All right. Sorry, everybody. I don't know what I did or what I didn't do. Okay, so
There.
so we're back. Did you see that one, Connor? The Fluence one?
Yes. Yeah, we
Yeah.
saw this.
Okay. All right. Okay. So Aqua then, so we have these services and they're sort of out there on the network. Well, then not just out there, there's a topology to it. And what we want to do is we want to compose the services into applications in that peer-to-peer highly distributed network. So you can't really, or you don't really want to use JSON RPC for that. You don't want to use your traditional REST endpoint approaches to it because it's peer-to-peer, it's highly distributed. And in peer-to-peer networks, as you probably know, nodes disappearing or going away for brief or even longer periods of time is more the rule than the exception. So it is expected, actually. So you need a lot of flexibility in how to resolve routes throughout the network, and it needs to be dynamic. And this is where Aqua comes in. Aqua is a purpose-built language for distributed systems, in particular peer-to-peer systems. And it allows you to basically capture those services on the right through a very high-level language that really unburdens the developer from a lot of the drudgery of peer-to-peer programming, and allows you to compose those services into applications. And if you do it right as a developer, actually decentralized applications. It's all open source, and we believe it really is going to commoditize peer-to-peer programming. And that's really what we want to talk about for the most part. Now, get into Aqua. On the bottom, you see a snippet of Aqua code. And basically, the first line basically says service. So what we have a service that's already deployed or will be deployed on the network. That's a greeting service, sort of a hello world. However, it's a fancy one. It not only takes a name, it actually takes a Boolean as well. And we see this in the greeting function. So basically the output, the expected output of this greeting function is where the string is for the name and the Boolean is for what we call the greet variable. If the Boolean is true, it says hi. If the Boolean is false, it says bye. And the string is whatever the name. So we get hi Connor, bye Connor, something like that. And in those first two lines, those are the service bindings. It's basically, if you're coming from blockchain, if you've done any work in Solidity, you can think of it in analogously as a ABI. And basically, it allows you to bind that interface to the remote interface and then start executing the associated functions. So right now, there's only one greeting, but there could be 10, there could be 20, there could be 5. It doesn't really matter. Then the next function, lines 4 through 8, this is actually the Aqua function that composes that service into something useful. And here we start bringing in the topology of the service. So if you look to the last two arguments in the function signature, node, and greeting service, node is basically the peer ID of the host for the service, which is identified by a unique greeting service ID. So basically what we're saying here is on that node, on this particular peer specified up there in that function signature, we bind our greeting service to that already available service through its service ID. And then we execute through that binding the actual function with our name and greet arguments. And then we get a result, and then we push this result back to the client. Now, if you look in the upper right, you see a sequence diagram. Basically, so the client could be a browser, right? It could be very, very thin IoT device. It could be just about anything. And it connects to a relay node. And then on that relay node, we determine how we need to call that service, what needs to be done. So the execution initially of this script, if you go back to lines 4 through 8, it's not on the actual network node. It actually happened on the relay node. And then it pushes it forward. And then on whatever node we have that service hosted, we start executing it. And then we get results back via relay back to our client. So the question you're probably going to all ask yourself now is, how the hell is that going to work? How does this happen? How do you make this work? And there is a foundation part that probably helps to understand if you want to work with Fluence, which we all hope you will. And this is called a particle. A particle is fundamentally a data structure, a conflict-free replication data structure that combines data and execution sequence and some metadata, which we can ignore for right now. The execution sequence is really important, and this is basically the compiled Aqua script. So if you think you program, this is your Aqua here, and now we compile that into what we call AIR. It's the Aqua intermediary representation, but you can think of it, it's not bytecode, it's actually a very Lisp-like code, but you can think of it as bytecode if you want to. And that basically is part of this particle. And what happens is that on every node, aside from the marine runtime that executes WebAssembly modules, through the linking into a service, we also execute the particle execution script on what's called the Aqua virtual machine. So it's also deployed on every node, and basically what it does, it literally steps through the execution sequence specified in the Aqua script, and then determines which services to call on this particular node, how to update the data, and how to then move that particle forward into the next service call. And that makes for a very, very different, very, very efficient request response model. And if you look at it sort of in a traditional, let me just go, it's okay. In a traditional model, client server model, you have a request response model that's sort of end to end, right? Service, an API, you get result back, you do something with it or not, and you just push it on to the next service and do some API, do something with it, blah, blah, blah. So if you want to put this in more context, let's just say you have a customer, and let me just go back real quick. Let's say you have a customer for which you have to do a credit check. And what you then want to do is you want to notify that customer with an SMS message of the credit check. So in the traditional client-server environment, what you would do, you would use your REST endpoints, and you probably go to Stripe, credit check or whatever, and then you get the result back to your client. And now you push that result into, I don't know, Twill.io, for example, and then the SMS message gets sent, and you close the loop with the client. In peer-to-peer, in particular Fluence peer-to-peer programming, this is not really how you want to do it. And back on the right side, the way the direction of particles are, what you would want to do is you would have a service. Let's just say that first service here is our Stripe call, which could be one of those APIs. You call that result back, and then instead of going back to the client, you put the result forward as part of the particle. This is where the update's happening to the next service, which calls, in this case, I think what I say, Twill.io, okay, and send the SMS message to the customer, and then you go back to the client, which in this case looks like two different ones, but it could be the same. And it could be a browser, for example. So you could actually, so if you had a CRM, browser-based CRM module, for example, you could use this model through Aqua to just fire it up and have a highly distributed service-to-service execution program model. What that helps you out is your load on the client becomes very, very small. You really enable very thin clients, and I'm not necessarily a browser or a mobile phone these days is a thin client, but a lot of edge devices are, and you can really enable a lot through smaller devices, thin clients with this kind of request response model. And this is why peer-to-peer to a certain extent is really sort of growing a lot of interest in, because it allows you exactly that. This is how you offload in a fairly fine-grained manner your workload from the client onto the network, literally onto the network. All right, let's go back forward. All this, of course, is the particle. Particle is, so you have forward chaining data movement model, if you will, combines the data updates and the execution steps to basically end up at the end of the script. So from to the little bit more applied, what I want to do is I want to talk to you a little bit and demonstrate what you can do with Fluence, and in particular with IPFS. When we say Fluence is a compute protocol, this is really what we mean. That basically means that developers are required to a certain extent to bring their own storage into their applications. And since we're looking at decentralized and off-chain applications, IPFS and IPFS related solutions clearly are sort of one thing you want to look at if you want to bring storage into a peer-to-peer environment. And where the demo gets interesting, or at least I think it's interesting, is basically what we can do is we can dog food our own Fluence stuff. So basically we can develop a service on Fluence, then store that service on IPFS, and then we can use Aqua to actually retrieve those WASM modules, deploy them to whatever nodes we want to, and then use those deployed services. And that's where we have a demo for. So let me switch to my... All right. Okay, let's just switch here. Okay, so I hope that I probably want to make this a little bit bigger. All right.
Yeah, we are still
somewhat visible
right now.
You still see the
yes.
slides? Okay.
Maybe, yeah, you just need to reshare.
How are we doing?
Yeah, we see the code.
Okay. All right. So the first thing I said we wanted to create a service. So let's just have a look at service. So services are comprised of WebAssembly modules, and in this case right now is created in Rust. And basically, it's your basic Rust. There is nothing super fancy. You don't have to use lifetimes. You don't have to use generics. You don't have to use any big traits or anything, because in WebAssembly, everything is values, so the underlying type structure is very limited. And so even if you're not particularly Rust, I really don't think you should be discouraged, because if you know Python or JavaScript with a little bit of digging, you actually shouldn't have a problem at all to write WebAssembly modules, at least of moderate complexity. So basically what we're having here, we're creating a module, and this module basically calculates the size of a file where the file comes from a file path. Great. Nothing, no big deal, right? So the only interesting part here, not the only, but the most interesting part here is that macro, it's called Marine, and basically what it does, it allows you to turn that Rust code into WebAssembly code. And it's WASI 32. So it's as I said, it's not WebAssembly bindgen. And we do have, let me see where I am here. So we have a build script for this, and I'm just going to quickly go through it. So basically what we're doing is this is the most important part here. We use Marine, which is a Fluence tool that extends the Rust compiler and Rust and Cargo to allow the WebAssembly compilation for our compile target. And then we do some stuff in terms of moving things around, so it's a little bit more accessible. So let's run that script. And I thought I had it pre-compiled, but I guess I didn't. So there you go. And what it's going to do is it's going to create this WebAssembly module that we will want to use in a little bit. Actually, like as soon as it's compiled, that's when we want to use it. Come on, come on. All right, and see, yeah, as we're waiting for this, if you look at the line below, what we're doing is we're copying that file from one directory to another, and this is really in your compile target. It's the WASM32 WASI file, and compile target. So okay, so now we have in that directory artifacts, we have actually our file. This is what we're looking at. This is what we wanted, and this is what we want to do something with. Now, I told you we're gonna take this this file, and what we want to do is we want to put this on IPFS, and then we want to use Aqua to access IPFS and do something with this file. which basically means we're going to calculate file sizes. So now I'm going to get a little bit lazy. And actually, hang on, I'm a little ahead of myself. So what we want to do is, so we need to get this file onto the IPFS node, on an IPFS node. And one way of, so what we did is we basically use IPFS as a sidecar to the Fluence node. And what I'm doing here right now, and I'll go through it in more detailed steps, is what I'm doing right now is come on. Okay. I'm trying to get the IPFS RPC address so we have the right node. And now I can go into the IPFS desktop. This looks a lot more complicated than it is. It really isn't. And we can hook that up. And there we go. And now we can actually put our file on there. All right, so I close this. Where was I? Okay. But if I ever remembered where I was, things would go a lot faster. Okay, this is the file we created. This is our WebAssembly file. This is the one we want to use. We want to put that on IPFS, and I already done this before, but I'm going to do this again, so you know there is no cheating going on. It's all like real and live, and a total high wire act, and no net. And we just drag this over here for now, and we got this new file here. All right, come on, show it. We needed to show up there. It needs to be not just uploaded, it needs to be actually processed, so we actually can get the CID.
Bernhard, I think your screen actually froze for a second here. Do you want to maybe stop sharing and reshare?
Okay. This is
Let's see.
sad state of affairs.
Oh no, the beeping.
Okay. All right, let me try again. So the beeping means no sharing. I think that's what it means.
It could be, yeah, it looks like your connection was a little shaky. All right, yeah, okay, it's back.
All right, so what I did is
maybe on a full screen this tab too. Yeah.
Do I want?
Yeah, can you make it bigger even? Because we still see air meet on half the screen.
Okay. Okay, I tell you what, I'm going to make air meet way smaller. And okay, so here we get so I put this this WebAssembly file onto the IPFS desktop. Super lazy, drag and drop. Turned out to be not that efficient, but yeah, well, maybe that was just the sharing. And then we get the CID from that file. So what we can do now is we can. All right, so now I lost my train of thought. Well, I didn't, but okay. So now what we can do is we can use that file and deploy it from IPFS, from this node, onto the Fluence network. So all we had to do was paste in the
I think you might be frozen.
The CID, and now we get the service deployed. Now let's have a look.
Hey, Bernhard,
let me try something.
I think you're frozen again.
Before, but
can you hear me?
I can hear you. So every time I open something new, it seems to be freezing things.
Weird. Yeah, let's try again. All right, that's better.
Okay. All right. So what we now have a service deployed to a network, and I got the beeping, which means we have nothing, right?
No, I'm still seeing it.
Okay. All right.
I'm
All
not
right.
sure.
All right. All right. We have the service deployed, and this is our service ID, and it's on that particular peer, which also happens to be the relay. And what we want to do now, the WebAssembly module, if you remember correctly, was we were actually calculating a file size, right? So what we can do now is we can actually, okay, I want to use a different file, just so.
I'm not sure why that's happening. It's very frustrating.
So we imported another file, which is called config.toml. It's right here, and we get our CID right for that file. So now we can go back to this little thing and say we want to get the file size, and now we have to put in the new CID. And now the very service we originally used, put on IPFS, then uploaded, is now calculating the file size. And hope you see the result. And we can double check that from the here. It was 116 bytes. And guess what? It calculated 116 bytes. So what we just did is we have a Fluence node. We sidecar that Fluence node with an IPFS node. We use the local IPFS desktop to store WebAssembly module that we created in Rust. We deployed that to that peer up here. And then we use that service right after deployment to calculate the file size of an arbitrary IPFS content addressable file. That's what we just did, and we got the result right here. Now, this is all nice, but what matters is how it's done. This is really what matters. And let me show you. This is where I really want to get into now. We want to look at so when you write code in Aqua, you have the option of compiling the file either into the raw AIR file or actually have it wrapped for you, ready to go as a TypeScript file. So it's super easy to use. And this is our Aqua file. So we have a bunch of aliases. Basically, a peer ID is a string, content ID is a string, multi-address, blah, 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 hash is all strings. So we just know what to use when we need to use it. And this is how you actually add a module to a host just using Aqua in essentially 3 lines. And this uses a bunch of built-in services that can be harnessed by Aqua, and this makes it super, super ergonomic. Now, I told you before that basically services are logical constructs, and the way this happens is that the WebAssembly modules, WASM IT, is nothing is shared between. It's a no-share environment, but they're linked. They can be linked through configuration files, and those linkages and those dependencies are defined in what we call a blueprint. And this is the way to create a blueprint using Aqua. Again, it's like 4 lines. And basically what that allows you to do is you upload your services, your modules, you upload your configuration for linkage among modules, and then you create one or more services which are logical constructs with unique service IDs. And that basically just tells then the execution model on how to call the functions from the different WebAssembly modules / namespaces in the Marine runtime at execution time. And so we create this blueprint first once we upload our modules, and then we bring it all together in how to deploy a service. And now we have the file size part, right? This is what we had before. And what it basically says is, remember we imported the content ID and the IPFS ID or multi-address. This is what we're gonna get. We get it from up here, and then we use it. And now we use some built-in services that are already deployed on the network to access our process files. This is the very here. Let me just go back to show it to you in the code. Here, this is the process Aqua, and this was the file size, and this is what we called right here, where we created the service and calculate the file size, and then it's just basically if the file size is successful, we do something here. It's called log size. Means coroutine, and log size basically is a callback. It's in Aqua we call it an error function, but it's literally a callback that allows us to update actually the browser with that result as we keep continuing with some other execution processes. And then at the end, you actually can remove the service, which if I'm a good citizen, I should do. But oh yeah, here it is. Here's the link. We can remove the service. And basically, we just removed that service from that remote node. And what we did is we basically linked a button to the execution model of this three-liner right here. So unless
Bernhard, do you want to try to stop sharing and reshare? Maybe see if the beeping goes away.
Okay.
I'm not.
All right.
Let's try. I've never had this issue before, but it's
that's just my luck.
a little distracting.
Murphy and myself were really tight.
Okay, I think that did it. Cool.
All right. Okay. All right. So, and these are just the data structures we've seen before, and this is the process file service we've seen before as well. Now, just sort of from an ergonomics perspective, I'm detouring a little bit. We have a REPL, and that allows you to inspect and even interact with your WASM services locally before you deploy them. And all I wanted to show you is basically this is directly from the WebAssembly module on my local machine, and these are the data structures and the functions that are exposed in the WebAssembly module for consumption. And since copy and paste is just so sad, right? We actually have the ability to export. Come on. Hey. Where's now the dog? UPS guy coming right when it's not a good time.
No worries.
And sorry everybody. And two German Shepherds poured out of their mind, and they got the beeping really got them psyched up. But so basically, what you can do is you can use Marine, which is also your compile tool, to export all your data structures and interfaces from your WebAssembly module into your Aqua files, and basically just pipe them in. So this, for example, this file, for example, you literally could just, if you pipe it in, this is your file to pipe it in, and then you end up with that. So this is like straight pipelining there. Okay, so are there any questions at this point? I know I went fast. I don't know. It's like...
I haven't seen any pop up yet, but yeah, I think it's a good time to pause. Someone did raise their hand a little while ago, but it might have been just about the screen. But all right, yeah, if you guys do have any questions, do drop it in the chat. Otherwise, I guess we can keep it going.
Okay, so if there are no questions, then there's sort of, I don't know. There's probably not much more point to delving into more detail on how the code works. The point is, you write a WebAssembly module in Rust.
Oh, we lost you for a second.
Lost me. Nice.
You're back though, but we're not seeing your screen anymore.
Yeah.
We did. Someone did just ask, is Aqua a different language?
Yes. So it's hang on, let me bring something up and reshare. Yes, Aqua is a purpose-built language. It's somewhat functional in nature, and it's designed to program distributed, in particular, peer-to-peer systems. It's a very concise language, and let me just okay. Now let me try and share again. Is that visible? Okay, so we got an entire book on Aqua, and basically, what it basically is a very it's super effective in doing one thing. It basically unburdening developers from having to deal with routes and general topology issues in order to resolve services as you're programming these systems. And it should look fairly familiar. This is how you define a struct or a data structure. It has collection types. It's fairly functional as I said, in nature. This is how you deal with various values, and it compiles into. Let me see. I'll show you how it compiles into an intermediate representation. And do you see this here? What I'm highlighting in VS. Okay, this is the intermediate representation, and this is what gets executed on the Aqua virtual machine. So, very long answer to a probably not that deeply meant question. Yes, it's a different language. It's a fairly new language. I think we released it March, maybe April. We've had Air before, but Aqua Air is, as you can see, anybody who's ever done anything in a Lisp-like language, and even with code completion, wrangling those brackets and semi-brackets is such a utter PITA that Aqua really abstracts over this and makes it like really, really nice to get a lot of things done. Up until Aqua, you had to write in Air, and even though it's actually kind of neat, it's just it's a waste of time compared to Aqua. So yes, Aqua is a new language, and it compiles to Air, which looks like this, and this is what gets executed on every Aqua VM, which is part of every peer in the network. Did that answer your question? Do you have any follow-up questions? Anybody else?
Yeah, it was super clear for me. Emmanuel, maybe we'll drop a note in chat.
Okay, so let me try and go back to the presentation now. Is that visible?
Yep, it is.
All right.
So there was a follow-up. Emmanuel said, so I'm thinking Fluence is like Kubernetes. Would that be correct?
Okay, so this is, analogies are extremely dangerous in many respects, because it's not a new field, but it's a new playground for most of us, because the closest most of us have gotten to peer-to-peer is literally through blockchain recently, and blockchain really abstracts the peer-to-peer part entirely away from it. I mean, the only interaction you usually have with peer-to-peer is when you curse at the logs, because the last three peers aren't syncing properly in your node, right? Kubernetes, yes and no. I think philosophically you can look at it this way, but we're not dealing with Docker containers. We're dealing with WebAssembly, And Kubernetes uses, through its structure, a highly, well, not highly, but a very centralized approach to orchestrate those containers for a variety of efficiency and execution arguments. The point, and I probably should have brought this up earlier, the whole point of Fluence is that it is highly decentralized. There is no brokers out there, no common brokers in there. And and basically you can look at it as an alternative to a variety of solutions, including some of the big cloud providers who provide open source solutions, which we feel benefits those providers a lot, but the open source contribution community not at all. And this is sort of philosophically, this is one of the driving forces behind this, where we wanted to have a decentralized model that allows a variety of participants, whether it be node operators, service creators, service users, and application developers, to come together in a fundamentally, you all going to crucify me for this, but fundamentally highly scalable network environment. Because unlike in blockchain, we don't rerun transactions. So you add a node, you actually add capabilities. You're not replicating. You're not strengthening the consensus. You're strengthening the execution capability of the network. That's really where it is. So I have said something like it's infinitely scalable. It's obviously not infinitely scalable, but it's highly scalable. And without a lot of sharding. And one thing we don't have right now, but that's coming soon, is subnetworks, and that really gives you sort of a sharding-like capability to carve out entire network sections. And in that sense, it's totally different from Kubernetes. However, the way you manage resources, there's a certain analogy, I think, that you can look at it to sort of capture your knowledge or transfer your knowledge into a new domain and understand what's going on. But it's not like Kubernetes, but there are aspects of it. Did that answer the question?
Sounds.
If not,
you got one more. Last.
Okay. Gas metric.
Can you hear me?
Yeah.
You got one more. Lastly, how does Fluence solve the halting problem? Like the EVM uses gas metric and all.
Okay. All right. So first of all, as I said before, we're not a blockchain. So nodes don't rerun other nodes' computations. So that's one. That's like a big difference. Second, we haven't implemented it yet, but one of the visions we have for the project is that basically there are licenses. So a node operator issues a license to a service to run and consume its resources, and there is going to be a payment capability attached to that. And that's entirely performance-based, because a highly capable node that allocates a lot of resources, obviously probably going to expect different payment than a smaller one, but that's up to the interaction between the node operator and the service provider, and possibly the application developer. So you have this intersection, and in many respects, it's not different how a cloud operator works, because you pay for the resources you consume, and that's it. And different cloud operators have different models to do it. So it's as I said, it's not a blockchain. And so why I love the EVM use gas metric, it's one of my favorite things. It's not as applicable in the sense that you have a finite set of opcodes you can spec out and then correlate to some payment metric. It's more traditional in that sense. Did that answer the question?
I think it did. Emmanuel, I can also pull you up on stage if you have anything you want to ask directly, or we can keep using chat. But just raise your hand if you're interested.
Okay, let me push on. If somebody either way makes him or herself known, I'll be ready to switch back. So just to go back, so we use Fluence node and IPFS node as a sidecar. We use those.
Bernhard, we're not. I don't know if you're still trying to share or not, but there's currently not screen up.
That share is not very Bernhard friendly. All right. So even though I haven't fully covered the slide, you've probably looked at it like 3 times because I tried to start it 3 times. So basically, in essence, you can use Aqua to program very different distributed systems through one seamless and what we believe is a highly ergonomic peer-to-peer or distributed network programming language. And that's really sort of the major takeaway. And in addition to Fluence's compute, you can augment the network with other peer-to-peer networks like IPFS, and in our opinion, get extremely nice results in terms of decentralization. That's extremely useful for off-chain compute and store for a variety of blockchains. And this is where we get into the prizes. Now, I got the short summary here, but actually I'm ahead of my time at least. I don't know, Connor, you can kick me off anytime, but I'm ahead of my timing here. So let me go to our repo.
Yeah, no, you're good. Take your time.
Fluence Labs. All right. Come on, read me. All right. So we got a variety of prizes. We have an early explorer or beginner bounty, which is super, in my opinion, super easy to do, and rewards you literally for just going through the quick start we have. And basically, what you want to do there is we want you to add an additional service to the already existing quick start services. You actually have to read it and look at it. And this is a very small bounty, but we have 10 of them for the first 10 people to do that. And I hope you're going to have a heck of a lot of fun with it. And anybody even looking at doing intermediate or advanced bounties, I think if you looking at that, you really should look at the beginner or early explorer bounty, because it's totally worth it, because you're already reading it. So you might as well get some prize money out of it. Then we have intermediary bounties. We get $2,500 each for 1 or 4 different tooling-like projects. The first was we'd be kind of keen to get we have an Explorer right now. It's a dashboard. It's a dash.fluence.dev. But we like to see how other people think about it, how they visualize peer-to-peer networks or distributed systems in general. And we would very much like you to use the Fluence service approach and the Aqua-based approach with IPFS, for example, as a hot cache, to and any web framework of your choice to build an alternative to what we have. And I believe there might be some really cool and interesting ways of looking at it, and how to query nodes for services and blueprints and all kinds of interesting information. Those services, for the most part, are already built into the node. So literally, you have to just look at the documentation and use Aqua to compose it, and build your interface around it, your UI. And so that's something that I really would like to see some innovation and from participants. Okay, I'm still there. I hope I hear the beeping, but I'm still there.
Yeah, we are. I do not know.
All right.
Maybe just share again. You stopped sharing. Yeah, maybe that's it. I think it's a connection.
I think
connection
so.
issue of some sort.
I always see green when I'm there. I don't know. Anyway, are we sharing again?
Yes, you are back.
All right. Then another project we'd be interested in is to, particularly in the Ethereum space, to port signature signing and verification services as WebAssembly service, WebAssembly modules and services, and provide some Aqua bindings on the workflows for at least sign and verify functionality. I got a few examples for you guys to look at, and I also believe it's not a super hard. I mean, it's an intermediate challenge, but there is a lot of room to really do something great. And particularly if you look at it from off-chain extension to on-chain capabilities, off-chain signing is a big deal, EIP 712, for example. So there's a lot that somebody could do to distinguish themselves and sack that prize, no problem. The third one we're looking at is basically, this is a little bit further out, and it probably requires domain expertise in either decentralized identity and or verified credentials. But I work in this area. We'd also be interested to see, particularly how you create, manage, and verify decentralized identity or verifiable documents and in a distributed environment. And particularly how you might want to use a linked data, IPLD, for example. And if you really want to go off and beyond, BBS Plus as the signatures would really score a lot of points, at least from me when we do the judging. And since I'm one of the judges, it probably would help. And the last one is ceramics. We've done some work with ceramics. It's built, if you don't know it, it's a super cool abstraction on top of IPFS, and that basically builds you an append log of immutable changes that lets you do really interesting things like actually create immutable NFT metadata. And what we're looking at is there's multiple ways to access and interact with ceramics, and two of them are CLI and HTTP. And those two we think are prime candidates for services similar to the IPFS one. So there's a lot of precursor work already done in the IPFS area, and we'd really like to see this ported to the ceramics environment. We have an advanced bounty, and this is basically a playground. If you're interested, it's $5,000. If you're interested in this, contact us. I have a lot of resources there. You can look at it, but if explaining this would take more than the 5 minutes we have left. But basically, we would like to see how Aqua can be created, checked, and executed in the browser, like a traditional playground. And we already started. We have some sandbox models for it you can use. And as I said, if that's something you want to work on, please contact us, and we'll work with you and make sure you really honed in on the task. And the last is more general use of any kind of the best use, literally, of Fluence in your dApp. $2,500, and we have some examples. Those are just examples, like decentralized NFT creation, indexing. There's the EVM, and then there's compatible EVMs. How do you route your contract to which? If you have one contract deployed on multiple EVMs, when do you use which contract? How do you index the results? And those are areas we'd be really interested in seeing people doing some experimentation and getting their feet wet. And that was it for our bounties. I'm super excited about them, and I hope you are too. And that's literally it from my end. So if you have any more questions, I'd be happy to answer them. If you want to think about it a little bit, or it's going to occur to you later, let us know in Discord. And other than that,
cool, awesome.
That's it from my end.
Great. Yeah, I see you just dropped that link. I also dropped the link on GitCoin to see all the Fluence bounties.
Yes.
Yeah, it looks like, we just got started yesterday. It looks like there's a few people doing the quick start one, but the other ones are wide open for the taking. So definitely go check them out and click start work if you are interested.
And on our resources, you can also book a Calendly, and I do believe we have the capability of providing a second workshop. So if there's enough interest on a particular topic, whatever, just let us know, or let the good folks at GitCoin know, and we'll try and figure something out and do something sooner rather than later. I know it's a hackathon, so the badge of honor is to do 90% of your work on the last 3 days, maybe the last two. I understand that. I've done this before myself. But if you haven't done anything in this space, particularly around Fluence and Aqua, maybe try to get in a little bit earlier. I truly believe it's going to be rewarding, because you actually are programming distributed systems. You're not using other people's work to use distributed systems. You program them. And I do believe that's the next generation in Web3. And anyway.
Yeah, absolutely. Awesome. No, I really appreciate the presentation. That was super helpful and in depth as well. I don't see any other questions. Last chance if there are, but Deepak just said, thank you, Bernhard. Nice introduction to the project. I'm new to Fluence and Aqua, but he started on the quick starter. So he said this was very helpful.
All right, cool. Well, everybody, thanks for being here. I hope to interact with most of you, or at least some of you, over the next few weeks. Connor, thanks for having us. We're super excited.
I guess actually that's a good point. What's do you guys have like a Discord, or what's the best community channel for people to?
We have a discourse. Hang on, let me just.
Let's see. Are they? Fluence.chat. I'll drop this here.
Right.
Yeah, Fluence.chat, right?
Yeah. And that just resolves to the.
Awesome. Cool. If you want to, if there's any other way you want people to reach out to you or if that's the best place, just, I don't know, feel free to drop in any other.
No, that's fine. We can take it from there. And of course, I know everybody's doing it, but maybe there's this one or two people out there. We're hiring. If we're hiring core developers, we're hiring in some of business and marketing areas. So if you like the project and think you're something interested in, please check us out.
Awesome. Cool. Yeah, it's a good opportunity. All right. And we're right on time, like perfectly well. Awesome. Cool. Well, thank you, Bernhard, so much. Really appreciate your time. And thank you, everyone who stuck around for the whole thing. We'll see you again soon.
All right. Thanks, everybody.